you go, or when you define the regions of an embryo from dorsal to ventral, there are different layers that will develop. And so this is a fate map that says the top part is going to become this region called the amnioserosa, and there's the dorsal ectoderm, lateral ectoderm, neurogenic ectoderm, and mesoderm. Don't worry about that so much right now. If we turn this embryo sideways and take a cross section, this is essentially what we see: mesoderm on the ventral side, amnioserosa on the dorsal side. Okay, so if we take transverse sections of a wild-type embryo, and we do immunohistochemistry for the dorsal protein, what we see is similar to the cartoon I just showed you here, where here in the nuclei at the bottom, you can really see the clear nuclei circles on the screens. It's really brown or orange at the ventral side, and not so much on the dorsal side. And here you see the dorsal protein is really more kind of diffuse out in the cytoplasm. Okay, so if you have a mutant embryo that is missing dorsal protein, you don't get any dorsal protein transferred into the nuclei on the ventral side. And all of these cells in this embryo will then develop into the dorsal back region of, or dorsal tissue, rather, because the dorsal transcription factor protein has not been translocated into the nuclei at the ventral side. Okay. Conversely, if you have a dorsal protein that, or you have a overactive toll receptor mutant, so let's say now the ligand, the ligand, is misexpressed and it's all over the embryo instead of just in the ventral region. Now you have an embryo where the dorsal transcription factor protein is localized into all of the nuclei, all throughout the embryo. And this embryo will then grow into basically a tissue of all belly, all ventral region, all all as a consequence of this translocation of the dorsal protein into the nuclei. Okay, so this migration of proteins is really important in laying down that first dorsal ventral body pattern. Okay, so this embryo is called dorsalized because it's all back, and this one is called ventralized because it's all belly, it's all ventral tissue. So here, and this is the dorsal side, and this is the ventral side. So dorsal is used in 1, 2, 3 different ways. Okay. So those are we've talked about maternal genes that are, when they're expressed as proteins in the embryo, they start to set up the initial anterior, posterior, and dorsal ventral body tones. So after a few hours, the zygote, or the embryo, is starting to translate its own proteins. So there are zygotic genes, so these are genes that are expressed in the new embryo, that basically respond to the patterns of proteins that were laid down by the maternal genes. Okay, so there are zygotic genes that are important for dorsal ventral patterning. And examples of these are twist and snail, which are transcription factors. And there's another set of genes called decapentaplegic, or DDP, tauloid, and short gastrulation. And these are signaling proteins. Okay, so these genes further cement where in the embryo the dorsal and the ventral regions are, and the regions in between. Okay, so for example, the The maternal dorsal protein that I just told you gets translocated into the nuclei at the ventral portion of the syncytial blastoderm, has control over expression of two of these genes, DPP and twist. And so here is an example of how a different concentration of this particular protein can have two different outcomes, or several different outcomes. Okay, so if dorsal is a transcription factor, and if it's expressed in high concentrations in the nuclei, then there's a certain threshold of dorsal protein that is required to get translation or transcription of the twist gene. So at this level of dorsal protein and higher, you're going to see twist being expressed. However, at a lower concentration, or in a region between the dorsal concentration required for twist expression and this yellow line here, this is the threshold of dorsal protein that is required for expression of DPP. Okay, so depending on the concentration of dorsal, you're going to have expression of twist or expression of DPP or nothing. Okay? So then this results in a different pattern of where DPP and twist are expressed in the embryo. So, for example, in the ventral region where there's high concentrations of dorsal in the nucleus, twist expression is induced. However, in the dorsal regions of the embryo where there's low levels of dorsal in the nuclei, or almost none, you see expression of DPP. Okay, but then there's a region where there's neither DPP or twist expressed, and that is also a response to these intermediate levels of dorsal protein in the nuclei. So this shows you how the concentration of a single protein can result in either this gene's phase, or this gene's expression, or this gene's expression. And if you just look at this embryo, you can tell that, well, twist is expressed in the ventral region, so it must be really important for the development of structures that come from the ventral side. Whereas the dorsal genes express DPP, and they don't express twist. So DPP helps cement that location is the dorsal side. And so this is a classic example of homomorphism. Okay, so then there's more. Okay, so I told you there's another set of proteins. SOG and tauloid TLG. So these genes interact with the DPP that has just been activated in the dorsal regions of the embryo. Okay, so here, as I showed you in the previous slide, dorsal is expressed mainly in